Hello, everyone. As he said, I'm John Adams. I was an early Twitter employee, and I'm the lead engineer for application services at Twitter. I also spend a fair amount of my time working in the security operations role there. I've been at Velocity and Web 2.0, and I worked at Inktomi and Apple and CNET and a few places before I was at Twitter. And in general, the entire focus of my team is to support the Twitter site, support our internal developers, and make the site performant and work on capacity planning problems. We spend a lot of time in configuration management. We spend a lot of time working on the existing architecture of the site, and we work with our infrastructure and performance teams to make the site run faster. Normally, this is my first time at USENIX, and I'm very, very happy to be here. Normally, I like to begin with kind of a look back at what's happened in the last year. And we've done a lot of work on specialized services for storing and maintaining the social graph. We have made Apache work much more efficiently for us. We moved to Unicorn, which is a different way of handling Rails requests. And in that time, we've added a lot more servers, a lot of load balancers, a lot of people who are coming into our ops team, and we have to work with them and make sure that they handle the problems that we handle with the same process and repeatability that we like to have. Just to kind of show you what I'm up against, we've got over 165 million users right now. Probably in the time that it takes to do this conference, we'll add a few thousand more. And of that, we're doing about 700 million searches a day on search.twitter.com and on the integrated search, which is on the sidebar of our site. And we process around 90 million tweets a day. It's well over 1,000 tweets a second. And the number is big. It doesn't sound that big, but you have to understand that when a message comes in, for example, let's say one message comes in from a Lady Gaga or Justin Bieber or Barack Obama, and then it goes out to 4 million people, the input to output ratio is pretty significant. Over the summer, we had the World Cup and we had the big NBA finals, and during those times, you see our traffic elevate up to 3,000 tweets per second. And these are major events for us. As the traffic increases, we have more load on our servers, more load on our systems, and we have to carry that request throughout the entire framework that runs Twitter. A really interesting fact is that unlike most websites, about 75% of our requests come in through our API, and this number is increasing more and more and more, and we tend to see the web requests being shut out by API requests. And of course, the first question is, why is this significant? A web request, an API request, one's over HTML, the other one's over maybe JSON or XML. But it's really significant to us because if you look at new Twitter, now this is the new two-pane version, this entire page is an API client. You connect to us, we send you about a meg of data, all HTML, JavaScript, and then from that point forward, the only communication that you're having with us is through very small, like 20 or 30K JSON objects. If you were to open up this page and view source, you wouldn't see a single submit tag. Everything is all over AJAX. So this is kind of a change in the normal model that we're used to on the web. We're used to the CGI model, which is easy to test, it's easy to debug. Scaling is fairly, it's fairly constant, but this is kind of the changing face of the web, and it's where things are going. We're going to see less and less of a reliance on CGI and more reliance on creating web applications that are very dynamic. On new Twitter, when you click on things, entire sections of the page slide in and out. There's a lot of custom work there in jQuery. It changes things from a security standpoint, like if you're displaying links, the JavaScript itself has to be secure. And it creates new challenges for scaling. So those of you that were with us back in 2006, 2007, you remember that we had, we do acknowledge that we had a fair amount of downtime and problems. And this has become kind of an interesting lesson in the way that you scale a website. We know that things don't work the first time around. You really have to plan, and you have to plan to build things more than once. The solutions that you're creating for 100,000 users or 500,000 users, or as you get towards the millions, these are entirely different solutions. You might be working with basic tools. Like this is a really interesting example. one thing that we discovered early on is that a lot of the things that we tend to rely on in Unix, they fail at large scale. Everyone uses cron. What happens when you have thousands of servers that are running cron, and the 0 second comes by, and you suddenly have a metrics collection event where you're going to ask each one of your servers to grab some data and stuff it into Ganglia? Well, when this happens, you will actually see a dip in request traffic because the entire architecture seizes and then does the job and returns back to life. Same thing goes for backup tasks. So you start doing tricks where if you want to run like a cron job over a long period of time, you end up putting in random sleeps, or you stagger the jobs based on the host name, or sometimes we'll do like an MD5 hash and then grab the last couple letters to just kind of distribute the load for scheduled jobs. Syslog is another pain point. Messages truncate if they're greater than, I think it's about 1,500 characters, if they're greater than the MTU of the UDP packet. You have data loss when the syslog server itself becomes overwhelmed. And if you are relying on things like RRD and Ganglia, or any of the tools that use the RRD backend as a time series database, the data rounding that takes place is fairly detrimental. Because when you want to go back and try to understand why you had a 1-minute outage 2 weeks ago, well, RRD's rounded the data away. So RRD is fairly important to us, and all forms of data collection are. Excuse me, I've been getting over a cold the last 2 weeks. It's been crazy. We came up with this kind of operations mantra that we exercise extensively in production. We use logs and metrics and a fair amount of science to find the weakest point in the application. We take corrective action against that weakest point using repeatable process. And we move on to the next weakest point. And we keep doing this over and over and over again until we get better reliability, more uptime, and for us, more tweets per second. And we actually do have TPS reports, so it's kind of funny. A lot of this, when you're collecting data, the big thing that you're working on in your site is this magical MTTD. What's the mean time for you to actually detect a problem in the infrastructure? And that being said, what's the mean time to recover from that failure? Okay, so this is it's a hard thing to understand that when you have a small outage, there might not be time to do a postmortem. There might not be time to get all the details you need to understand what has happened to the site. And we just have to get the site back online. So we are working in kind of a model where we assume that we can lose a significant portion of the infrastructure and the site can remain online. This is kind of a change. People in the enterprise world don't really think that way, at least in my experience. The assumption is everything has to be up all the time. And we're OK with having stuff go down, provided we have fast ways of recovering from the failure. So as far as recovery goes and sort of configuration work and how we manage things, one thing that I'm going to say over and over again throughout this presentation is that we don't think that people should be just systems administrators anymore. I'm a very strong proponent of DevOps. We look at systems management as a solid programming task. You can use Puppet, Chef, CF Engine if you're still using CF Engine, and we want to look at the overall way that we do business of running the site, and we don't want to silo information. We recently held a hack week in which people from different teams exchange data. People get together. We'll combine developers with one ops guy. We'll dedicate ops people to different teams, and we want to end this sort of grabbing a piece of the infrastructure, a new piece of software, throwing it over the wall, and not knowing what had happened to that code. We don't want to be in a position where the operations guys are in the dark and where they don't understand how the system works. This is something that's been going on in IT for a long time, and it really needs to end, and we need to work together. When you look at systems administration in this way, you sort of move from I'm the guy who installs things to I'm the guy that does large amounts of data analysis. And we understand that when you instrument the world, it really pays off. This is a great quote, and I've had this in my slides for a while. Tim O'Reilly says, analysis, visualization, and other techniques for seeing patterns in data are an increasingly valuable skill set. This is going to change the way that we manage systems. Okay? So we graph everything. we probably have 30, 40,000 points that we monitor. And frequently there's a sort of Heisenberg effect where, like, as you monitor more things, maybe the monitoring actually incurs a load. So this is something you have to think about when you start to create extensive levels of monitoring like we have. If you are in the fortunate role of developing tools against our API, you should monitor us as we monitor the site itself. We have a couple publishing points where we advertise dev.twitter.com. We have a complete API availability section there, and status.twitter.com where we have our communications team post things about the site. And the source of that data is coming directly from our monitoring systems. You also enter kind of a different role as well, where maybe instead of just being the guy who is developing the software or being the systems administrator who's running the software, you start doing profiling. And we have a lot of tools that we really like for this. We will monitor memory leaks and latency. We'll look at strace, for example. Like maybe we want to understand if an application is running in a tight loop, or maybe it's got too many file descriptors open. We're big fans of YCanalyzer, which is a network analyzing tool written by Yahoo. And we'll do some things like maybe we're having an issue with memcache. We want to look at what the response time of memcache and how fast are connections being closed, how fast they're being opened. And with TCP dump and YCanalyzer, you can get a really wonderful insight into the size of packets and the rate of connections and the rate of SYNs. Another not so often used tool at Twitter is the Google perf tools. We've got some patches that allow us to use perf tools with Ruby, and I'll get into that in a little bit. We can actually introspect into our Ruby processes and understand what's going on inside of the application server. When you collect this data for long periods of time, you get to do things like this. Like, we had this thing happen called the Twipocalypse. And, excuse me. The Twipocalypse was when the identifier for a tweet passed the signed integer points. We actually passed 2 to the power 32. Well, actually 2 to the power 31. And we were able to collect data from our databases and look at the rates of traffic and say, when are we going to hit the next one? Because obviously we're growing so fast, something bad's going to happen. And we said, let's calculate when we'll hit the unsigned integer, the 32-bit number. And we were able to predict this using curve fitting in Mathematica, or you can use cfit-yk or R if you're familiar with those tools. And we were able to predict when that failure was going to happen within a few hours. So that was extremely handy. You can do this with disk space. You can do it with network loads. You look at your daily peaks across a month, plot those points, calculate that point out into the future. It's fairly basic statistics, but it's crazy powerful. One big thing is that you don't really have to pay much for these tools. cfit-yk is open source, R is open source. All right, I'm kind of jumping around here, but so another big lesson is that can I get a show of hands? How many people here are currently using a configuration management system? That's good. It's about 60%. For those of you that aren't using a configuration management system of some kind, you need to start this yesterday. The sooner you start using configuration management, the less work you're going to do in the future, and the less mistakes you're going to make. If you want to sit down and deploy 1,000 web servers that all work in exactly the same way, you can do that with imaging, and then imaging is going to fall out of whack because you'll have your known good image. Some time will pass by. The known good image will go out of sync with the older servers you've installed. And if you're using Puppet or CF Engine or Chef, as you make changes to your production infrastructure, it's happening on all your systems at the same time. We started this about 2 months into Twitter. It was just before I got there. I've been there for about 3 years. We use Puppet. We really like it. We've had our share of problems with it, but we've managed to get around most of them. If you are working with Puppet or any of these systems, and you have a version control system, like SVN, you can start adding on wonderful little things to your system. For example, let's say your administrator wants to go and make a change in DNS. Well, instead of putting the DNS file directly on the servers and then crashing named and then your production infrastructure comes down or no one can reach your site anymore because your DNS records are bad, you're able to go and hook in post-commit hooks into SVN. So you can run named in a test mode. You can verify that for example, the serial number of the SOA record has been updated. You can run all of these consistency checks, and then if they don't pass, you reject the commit and you don't allow that admin to modify production. So this starts to bring in the notion of kind of quality assurance and automated testing into changes in a production environment. And for us, that is just such a huge win. I would say that a fair amount of our outages in the first year were caused by human errors because we didn't have these tools in place. One other big factor is this stops people from logging in the machines. If anyone's logging into a machine to make a change, something's wrong. Your configuration management system is not supporting that section correctly, or you don't have a module. We've seen a couple instances where instead of someone writing a module to go into Puppet to manage our systems, they'll go in and make a manual change on the system, and they'll take a file and change it, and then they chatter +I to make it immutable so that the Puppet system can't come by and stomp on the change. So at Twitter, we have this saying, which is that you can't chatter +I with broken fingers. It'll break your fingers. Very simple. OK, so Puppet gets fed by this wonderful little tool that we wrote called Audubon. And Audubon is our machine database. And there's a tool called Loony, like a crazy bird. And Loony connects to our machine database, and it ties into LDAP, and it allows us to do things en masse across the infrastructure. This is sort of in opposition to the notion of Puppet, where we say, Puppet, I've got my centralized configuration management, and then with Loony, you're able to invoke mass change. But typically, we only run Loony if something has gone extremely wrong, or let's say we need to force a Puppet run on a particular subset of servers, or we want to use it for like machine data acquisition, like tell me every machine in my cluster that is a mail server that happens to be running Red Hat Enterprise 5.3. So we can do those kind of queries using this system. Having a centralized machine database is key to running a large infrastructure. Excuse me. Once you have a machine database of this kind in place, you can handle asset management, you can handle machine intake, and this might be as simple as you're building one MySQL table that has your machines in it, and then you're writing a very simple command line shell script that asks the machine database, tell me all the machines that start with this name. At some point, we'd like to open source this system, but it's kind of janky and not ready for prime time. We have open sourced very large amounts of our infrastructure, though, and I'm going to talk about that pretty soon. OK, so this is something that a lot of people have asked me about that ties into our machine database. And this is murder. And murder as in a murder of crows, not kill every sysadmin in the building. We've managed to move our deploy system to BitTorrent-based deploys. So this is a wonderful, legal, awesome use of this technology. We can deploy to thousands of machines in anywhere from 30 to 60 seconds. And the subset of machines that we actually install software into gets determined by the entries in the machine database. We have open sourced this, and that's available on our open source site, which I'll give you the URL for if anyone's interested. This being said, there are a lot of issues when you move to a centralized management world like we have. You may have eliminated the problem on the single hosts, but frequently we introduce new problems. The environment that we run is very complex. I would say that our Puppet install maybe has a couple hundred modules in it. The modules are, if you're familiar with Puppet, there is a module, and the module is a class, and the classes have dependencies on other classes. So maintaining the centralized management store, where all of our Puppet data is, starts to look a lot like managing a very large software project. And with that, you need developer tools to make sense of that code. We probably have around 40 admins, maybe more, and all of the engineering team has access to modify our Puppet configuration. So what do? You know that if I make a change to one system and you make a change to another, we're going to create all kinds of unknown interactions that didn't exist before. So putting a second set of eyes into the problem solves it. So we use ReviewBoard. And ReviewBoard is a system for displaying diffs, and allows people to comment on diffs and highlight sections of code that they might not agree with. And ReviewBoard's open source, easily downloadable from the internet. And the big thing with ReviewBoard is that we actually put hooks in SVN that when you make a change to the Puppet infrastructure, it publishes directly into ReviewBoard using the ReviewBoard API. And then everyone on the operations team gets an email, and then everyone can say, do I agree, do I not agree, ship this, don't ship it, here's why. So you can see at the bottom of the screen there, I have a little ship it, and I say, oh, I think this is OK, but make sure we don't blow up the search engine. This is a very powerful tool. It's a complete review process for sysadmins. Our typical mode of operation is that once we have a reviewed change like this, we will only deploy the change to, let's say, 1 or 2 representative hosts in every machine in our infrastructure. So 1 DNS server, 1 mail server, 1 web server, all the way down the line. And we reset them, load this new configuration. We allow Puppet to run. And then we sit there and we watch the error rate, we watch the logs, we make sure we haven't killed the site. If we lose that 1% of machines, we don't really care. You know, chances are we can still run and our load balancers will take care of things. So, excuse me. So, how do we find the errors? Like if a sysadmin makes a change, normally we might rely on syslog. We might want to look at the, let's say, 500 rate or 4xx rate coming from the server. Well, you know, in general, a syslog just does not work very well at the loads that we're working at. And you know, if you lose your syslog server and a system comes back online, it's not going to go back in time and resend the logs for the last half an hour to that server. Those logs are effectively lost. So we've moved to Scribe. And what Scribe is, if you're not familiar with it, Scribe's a product that Facebook wrote. And what Scribe does is it is a very simple Thrift service that accepts a message and a category type. And in the event that a Scribe server goes away, so if a Scribe server is sending to a master, because it has this master-slave relationship, the remote Scribe server will actually go back in time when the master comes back online, and it will send all of its logs back to the master. So there's a very, very nice system for dealing with lost log messages. And we went ahead and we made a bunch of patches to this because we had sort of this holy grail in mind. And that was, what if we could take the logging system that we have and send those logs directly into Hadoop? Because now we could do very fast online processing of log messages without having to pay for a tool like Splunk. Now, admittingly, Splunk has a lot of features in it, like algorithmic detection and keyword processing, but we wanted something that could take advantage of our existing Hadoop cluster. So what we did is we patched Scribe to compress data with LZO in real time and send it across our network to the Hadoop cluster and write directly into the HDFS file system. And we do this with almost every single log that we have. So you get to write pig scripts. You can write Java code against the Hadoop libraries to parse through this data. And it's really, really simple to work with. You know, and once the data is in HDFS, it's incredible, because now I can get aggregate reports using MapReduce. You know, I can say, give me every server in my cluster, tell me everything that's going on, and give me my error rate in the last 5 minutes, 1 hour, 2 hour. Or, for example, in the case of a particular controller, like we have a lot of abuse that happens on the follower controller. There's these sites that will create things like get followers fast. You know, you sign up, and then they'll thrash around your account and add followers and delete followers. So we can get reports that say things like, tell me how many people have called that URL in the last hour. How many unique IPs have been there? What did they do? Why did they do it? And this is just part of a larger effort for us to actually take the data that we have and turn it into just actionable information. We always want to know where the code base has gone after deploy. We always want to know what has happened to our site. And we use these metrics to get us away from a world of get us away from a world of firefighting and move us into a world of solid capacity planning. One output of this system, which we use, is we have a dashboard. And on this dashboard, we sort of have our top 10 metrics of the site. We do a couple of interesting tricks here. If you use Google Analytics, we will actually do things like use Google Analytics in reverse. Many people are interested in the fact of how many people are coming to my site, what's going on. And we'll do things like put Google Analytics on our error pages or like on the whale page. So that when that page loads, we can actually tell how much time was lost by people accessing those pages. We'll also pull in data from managed services, hosting providers, advertising providers, and we will advertise these metrics on very large displays in the ops area. So you have about 3 or 4 big TV screens. If you don't have a dashboard for your site right now, you should make one. This is a simple one we did with just HTML and direct access to RD. But if you have something more complicated, maybe you're using Cacti or another system, you should get this data as soon as you can and advertise it to everyone, all of your engineering department, everyone in ops, and advertise the application level metrics to everyone in your business team. For example, you might see, your business team might see a dip in, let's say, logins per second, or the number of accounts that have been signed up per day. And the ops and engineering teams can work with them to tie that number back to things that have happened in the infrastructure. Maybe there was a deploy that went out that actually made things worse. We also have a bunch of scripts. Like, we have this wonderful thing called the Whale Watcher. It's pretty simple. We look for error rates on the site, but they're aggregate error rates across all of the web servers that we have. And for those of you that have seen these errors on our site before, the whale message is a 502 or a 503. It's effectively when the front-end systems cannot reach the back-end application servers. And the, the robot is a 500. That's when we've actually made a mistake in the code or something has failed. We use these metrics fairly extensively to block deploys. One script that we have as sort of part of our application deploy process is to grab a sample of the data set. Tell me all the data running through our system right now, and then we will verify that our production server is fine, that the canary hosts, and that's the 1% that I mentioned earlier, that they're all okay. And only when we can clear all of these known green lights, this is the sort of NASA go or no-go decision. When we can clear these conditions, we then have a chance to go ahead and execute our deploy. So that one step right there has probably saved us from incredible numbers of outages. Because if I can predict in advance if my site's going to fail because of a recent deploy, and I just don't deploy at all, site stays up. Another thing that we do is we've modified the header stuff in Ganglia and on a number of our pages to actually display the last deploy times for each of the infrastructures that we have. The advantage to that is that everyone knows exactly when the last deploy went out. If you are tracking this type of information, and for example, you have your network bandwidth graphs or your request per second graphs, and you can draw lines in the graph when the deploys went out, you have a very wonderful picture of telling me, to tell your team, this deploy went out at this time, our traffic dropped by this factor, it's your fault, roll the deploy back. It's very, very important to keep track of deploy times in a visible way. Okay, so what happens if we make the fatal mistake and we launch code? We have a rule generally that says for every feature that you want to deploy at Twitter, it's got to be wrapped up inside of what's called a dark mode or a decider flag. And what this is it's basically a value from, I think it's like 0 to 10,000, with 10,000 representing 100% deploy. And we have hundreds of switches in the site that we can throw. And as we throw these switches, major features will turn on and off. You may have seen this recently when we did the deploy for new Twitter, where we were able to roll out the site in incremental percentages. We started around 5%, and then after 2 weeks of time, we were at 100%. This is effectively the emergency stop button, the big pull chain on the assembly line that allows us to recover the site. We can also put portions of the site into static or read-only modes, where instead of the request hitting our back-end servers, we send the request directly to cache. So that's kind of my review of how we, how we deploy and kind of manage the sysadmin side of things. I want to kind of pull back the curtain a little bit and let you see how we manage things from kind of the request side. Like most sites, we have a pretty standardized request flow. We have load balancers on the outside, many, many load balancers. We have Apache. We run Rails. We have specialized internal systems like FlockDB, which is a social graph database that I'll talk about in a minute. And we have a message queue called Kestrel. And we also use memcached and Cassandra and Daemons and things like that. Almost every portion of this infrastructure is available in some way as open source. And I think that's one of the greatest things that we have going for us is that we're willing to share that code with the community, because we've taken so much from the open source community to build our site, and we want to give it back. So This request pipeline is interesting because, as you know from running a website, the request pipeline is it's an interesting source of pain and problems. When you deal with Apache, you have to deal with like the number of threads, the number of clients that are available. You're frequently fighting if you proxy into an application server like Rails or Jetty. You're dealing with contention there. Memcache, we discovered many things about how memcache performs with extremely large numbers of connections. And database connections are a scarce commodity that we don't want to use that often. So a lot of the work that the ops and dev teams do is to go through this kind of pipeline and identify where the bottleneck is, increase the resources available, or rewrite that piece of software and move to the next step. So last year, we had a really interesting experience where we moved from a sort of traditional Rails server called called Mongrel, to a server called Unicorn. And Unicorn is interesting because the standard model with Mongrel is that you have, let's say, 16 servers on the back end, and you have Apache connecting through mod proxy balancer to those 16 servers. And then as you consume more and more resources, the connections backlog against those 16 mongrels. This is actually a very poor model. It's very similar to a model employed in every grocery store in the country, where you have no idea, well, maybe you do, how many items the guy has who's standing in front of you. You don't know what the depth of his work queue is because you don't know what's in his basket. If you look at, like, let's say a store like Fry's or any store that sort of implemented this serialized queuing model, you line up all the people behind one gate, and then as resources become available on the front end of the system, you open the gate and you release the work. So Unicorn does that. It has a single socket model where it grabs the next request off the top of the queue, and this is a lot better than the way that the default Apache proxy system works, where it's just fling the traffic at the back end and hope to God that the listen queue doesn't back up. This got us about 30% more CPU on the front end, and it cleared a lot of bottlenecks in the Rails workers. But that being said, 30% of Twitter is maybe a week, maybe 2 weeks. So we're constantly looking for advantages like this to get more traffic through our existing systems. And as you know, when you're building out an infrastructure this rapidly, a number of problems that you deal with are kind of basic issues, like cooling, power, rack space. How do you get all these servers in place? So any optimizations we can make to utilize that system, to utilize our existing systems in a better way, is a huge plus. Also, if any of you are running a mod proxy balancer in Apache like 2.2.11, I found a set of really horrible race conditions that I had to patch around the way that balancer counts function. So come up to me later and we can talk about that. This is a race condition that actually causes workers to not be properly utilized on the back end. And the way that I even found this problem at all is that we are working at such high scale that we can actually exploit race conditions in the web server. This is kind of crazy. Like, you would never see this if you were a normal user, but it affects us. Okay. Another myth I kind of want to dispel is this notion that Rails is not scalable. A lot of people say, oh God, you're running Ruby. It's no good. Rails runs the front end of Twitter, and the back end is written in Scala, and we have some Java out there that manages a lot of the back end resources and daemons. Any application server like this has a tendency to write bad SQL, to not cache things correctly, to maybe stall on garbage collection. Java is always a good one for having that problem. And we may even have replication lag that causes the front end to back up or issue invalid data. There are ways around this problem. Frequently the way that most people get around it is they'll use memcache. Memcache, we have probably terabytes and terabytes of memcache out there. I think maybe the only person who has more memcache is probably Facebook. This leads to an interesting cultural problem when you start deploying lots of memcache, because there tends to be this belief in the developer community that I'll just keep putting things in memcache. And the more things I put in memcache, the faster the site will go. But you learn quickly that this network memory bus thing is not infinite. There's a reason why we have onboard hardware. as you begin to shuttle more and more and more data across your network, and you store more things in memcache, you start to have more evictions and more TCP retransmits. And going back to what I said about Y Conalizer, TCP retransmits are one of the things that we can detect while doing packet analysis. So if you're looking at the network stream and you look at memcache, you can go, oh God, this memcache server is really failing in a horrible way. And you may not even know it until you start to look at what the network is doing. If you fill up memcache to the point where any single slab in memcache is overloaded, what happens is you start to have evictions, where the system says, well, this slab is full, I'll LRU the last cache, throw it away, slab goes missing, and now you get a database hit because you have to go back to the database and get that data again. So one way around the memcache problem is to start segmenting pools into things. Like if you are storing sessions in memcache, put it on a completely independent pool. Don't put it anywhere near your main memcache pool. If you are looking at the way that, for example, if you always store the same thing in memcache, maybe you're storing a user object that is of a consistent size, you might want to actually go and look at the flags on memcache and make sure that you're allocating memcache in such a way that you are getting the most number of slabs at the particular size of object that you're storing. Frequently, people waste a lot of memory in memcache because they run it with the default parameters. We also have a tool that we wrote, again, open source. It's called PEEP, and PEEP will actually dump core on a memcache process and allow you to walk the entire tree and figure out what the optimal size is. This is a great tool for optimizing memcache. So memcache is kind of a good lead-in into another sort of central way that we admin systems, which is that we're looking always for opportunities to decompose the app. If you have an application that does login and it sends mail and it does many different things, it sends a tweet, maybe it sends an SMS, it's in your best interest to find out how you can abstract away all of that functionality into separate systems. If you start to decouple services from one another, like login is only dependent on users, sending mail is only dependent upon a mail object that tells mail where to go. It's not dependent upon the users and the database and the follower graph and everything else. Decomposition becomes very powerful. It's not a good idea to build monolithic apps. And from the systems admin point of view, as the developers decompose your app into smaller and smaller components, you get to build out server farms that have that one particular API call sitting on a farm of, let's say, 20 or 30 boxes sitting behind a load balancer. If you happen to lose a login system on one box for 5 minutes, who cares? You've got 20 more boxes dealing with the problem. Of course, how do you decompose requests, right? The sysadmin has one problem, and the developer has another. From the systems administration standpoint, it's in your best interest to get requests out of the pipeline as quickly as possible. The simplest example I can give of this is when you send an SMS on Twitter. We don't, you're going to put in your SMS, like let's say you send me a direct message. I'm not going to do anything with that message except restore it. I'm going to enqueue requests that say things like, when you get a minute, when the SMS subsystem frees up, go ahead and send this message. Same thing with email. We don't have any direct SMTP connection on our mail servers between the mail servers and the web servers. We enqueue a request because we don't want to waste any time. We want to get the data back to the user as soon as possible and drop the connection and go on to the next guy. So we do that with queuing and Daemons, and we also do it with Thrift. And Thrift is a fairly awesome cross-language services framework, originally developed at Facebook, and now it's an Apache incubator project. Almost every language, with the unfortunate exception of C, is supported. Although I suppose you could kind of call C++ from C, which gets really scary. But we abstract a lot of our services away into individual Thrift calls. So, for example, if we want to find out how many users you're following, we make a Thrift call. We don't run any of this on the web servers. We have a secondary system. So Thrift is sort of our RPC mechanism. You may be familiar with things like Google has protocol buffers. There's Avro. There's a bunch of different solutions to this problem. But we like Thrift because it's simple and it's cross-language. Another way we solve this problem is with Kestrel. And Kestrel is an open source message queue that we wrote in Scala. It was originally written in Ruby. The thing about Kestrel is that it looks like memcache, it smells like memcache, it's not memcache. If you execute a set against the Kestrel, because memcache is a key value store with keys and values. If you execute a set, it's an enqueue. If you execute a get, it's a dequeue. We don't care about how jobs are ordered. We don't share state. We do persist to disk, but we persist to disk in completely isolated threads. So as requests are moving in and out of the daemon, they don't impact the current load that the daemon has to process. And attached to this Kestrel are these daemons that do things. So we might have a daemon that sends email, another one sends SMS. This was an interesting point of contention for us in the first couple of years because we actually had daemons that would bloat memory, that would leak. We introduced this thing called the seppuku patch. It's like, And if the daemon ran for too long or it got too big, we would just kill it. And we would kill it after a certain number of requests. And the long-running leaky daemon problem created low memory instances on many of our daemon hosts. And this pretty much would take the site down on a regular basis. One sort of advantage of running daemons, though, is that let's say you post a tweet and the daemon isn't there to process the tweet. It affords us an interesting failure mode, and that is that your timeline might delay rather than just outright fail. So if the timeline begins to delay by, let's say, a minute or two, we'll sound alarms, and we'll have people's pagers going off because this is a condition which should never happen. But for the end user who clicks reload on their phone or any type of device, their web browser, they don't really see it, unless they have a lot of friends. For me, I follow probably 1,000 people, and my Twitter timeline kind of looks like IRC because it scrolls so quickly, especially when I'm at a conference like I am now. We did a lot of consolidation work in the daemons. We kind of went to having a single daemon be able to process multiple types of jobs. This was great for saving memory because we don't have to run that many Ruby instances. Kind of a big win from the system standpoint because it gave the systems admin team a lot less to manage. Okay, so another really big win in the last sort of 6 months. We invented a sharding layer called Gizzard, like the nasty bits of a bird. And what Gizzard does is it allows us to take data. Like most people do MySQL sharding. You can do functional partitioning where you have a different MySQL database server for every type of object you're storing. You might expand those things into masters and slaves, which I'll talk about in a minute. But our sharding framework allows us to take a data set and shard it across hundreds of hosts and thousands of small tables. It's still MySQL. It's, again, open source. The big thing about this is this abstracts the entire sharding problem away from the developer and away from the sysadmin. If you call into Gizzard and you ask it for data, it finds the server and hands you the data back. I think sharding is a hard problem for people. You have to come up with a way of doing sharding. A lot of the schemes simply don't work. Some people will do things like shard based upon the modulo of the user ID. This is a truly horrible thing to do because as you add more servers, the modulo goes out of whack and you can't find your data anymore. Frequently in sharding systems, you have to figure out how to expand and how to move hotspots. I remember a funny story from John Alspaugh, who was the admin at Flickr. He's now at Etsy. And he talks frequently about a server they had called ShardForce 1. And ShardForce 1 was a server that all of the White House and Obama data lived on. And it's a hotspot because you have this one user who's very popular, and all of your traffic goes to that single place and then crushes the server. So Gizzard tries to fix that problem by distributing data for single users as well as multiple users. Okay. So this flock system is used to store our social graph, right? So what's the problem with social graphs? If I tell you I have 190 million users, and I tell you that they're going to follow, let's say, everybody at least once, it's 190 million times 190 million equals, oh my God, huge database. These operations, the sort of order, X by M, massive, massive social graph, this creates a real problem. And I think that the current wave of Web 2.0 websites is just completely not possible without massive amounts of memory. Of course, if you run a site where people can follow each other and then not do anything for a long time, it's pretty easy to get away with large amounts of caching. And for us, we're the real-time web. So how do I cache when my TTL is way less than a minute? Well, we have ways of getting around that problem. There is opportunity for caching frequently. And even when you do cache something for a minute, it can remove a very large amount of load from the site. We also maintain libmemcached. We're probably the biggest maintainer of that library. And if you're currently using MD5 for your hashing algorithm in memcache, you might want to take a look at FNV. It actually is much less computationally expensive, and it can save a lot of load on your memcache servers. Going back to what I said about the network memory bus, caching everything is not the best policy either. Maybe you can't invalidate caches fast enough. What happens if you put yourself in a situation where you've got your entire user database cached and you have a power outage in your main data center? Your site's going to go down for like 8 hours. You're not going to recover unless your databases can take the same load that the memcache servers could take. Perhaps you're running in a degraded mode, but from the administration standpoint, you need to be in communication with the developers and say, look, I see too many hits coming to my memcache servers. When I go back to the database, the site fails. So we sometimes feel that frequent testing of the of memcache failures is a good thing. We've done things where we would IP tables off the memcache port just to see how the site responds. So be very careful with your reliance on major caching systems, or have a lot of really fast power backup and generators available. So our MySQLs with Gizzard and memcache on top get used more and more and more as sort of a key value store. We have a general hatred for joins. We would rather have people do that in the application layer. And sharding frameworks don't like joins either, because you might have servers in multiple locations that you have to place together, and it's very hard to join data across data centers. The challenges that we typically run into on the MySQL side are things like replication delay. You'll notice that kind of out of the box, MySQL has only one thread for replication. It's very, very, very slow. We will typically do things like delayed inserts into those databases to make sure that we can write data without having to block on that write. And in general, we find that you have to use specialized databases to store things like the social graph. Doing like end-by-end traversals inside of MySQL is no fun. And that is probably one of our main driving reasons for building out FlockDB. This is like an interesting set of optimizations that we came up with over time. Benchmarking your data set on different file system types is a big win. Figuring out what works best for the disk scheduling algorithm. Definitely disable A-time. Like mounting your database with A-time turned on is a death sentence. You really don't need to know what time the InnoDB file was accessed last. It's just pointless data that causes an extra write on every disk transaction. So a lot of our issues centered around the way that we manage users and statuses, and we're moving more of these things into our sharding layer as time goes by. Another practice that we instituted from the administration side of things is using mkill. And there's a series of database tools, and what mkill does is it looks at the database process list, and it says, how long have these jobs been running on the database? If a job runs for too long, mkill will wake up and it will actually just kill the process. So it stops that query from occurring. This is kind of interesting because the first thing you think about is, well, what about data integrity? How can you arbitrarily issue kills inside your database? Well, we kill selects. And we kill them because as the database issues table locks for all the rows in that table, as it's building up its response to the select query, you have a massive degradation in database performance. We also use this to find other things. Like we had an issue once where Rails inadvertently issued a update users set password equal foo across 190 million rows. If that database query had actually finished, which it never would because it would take days to run in our infrastructure, we would have lost every user account in the system. And mkill logging and detection was able to stop that query and find the bad piece of code, preserving all the accounts on Twitter. So these are very, very valuable tools. And don't be afraid to pull the chain on the developer and stop this from happening. Generally, any query greater than a couple seconds is a bad thing. Okay. So key points to kind of take home here. We don't think databases are always the best store for the job. Sometimes you will have to write something, but you can still use databases as a backend if you need to. If you're an admin, instrument the hell out of your site. Collect every piece of data you can. And take those metrics and use those metrics to make solid decisions and not guesses. And when you can, don't make services dependent on each other. And move as many things as you can into an asynchronous job. It's saved us, and it will save you. Okay, I think we have about a half an hour for questions. So if anyone has any questions, come on up to one of the microphones.
Hi,
Is his mic on? I can't hear him. Oh. Did you kill? Oh, okay.
Go ahead. Just please say your name and where you're from.
He said, please say your name and your affiliation and where you're from.
I'm Jay Faulkner with Rackspace, and you kind of laid out a very good idea of an end game, but what did you find were some intermediate steps that you took as Twitter to kind of go from unscalable to somewhat scalable before getting to kind of the holy grail that you've described here?
Well, I'm sorry I didn't make that point clear. The biggest thing for us was going through and doing very extensive data collection. I think that when people are first working on a site, the time that they are spending bringing that site to market and trying to get that thing online, that's their main priority. Their main priority is get the application out the door and get it running. And for us, we didn't have as many metrics as we would have liked in the beginning, so that when we had a failure, we could not identify where the failure was. So this is an iterative process. As we add more metrics to the system, we begin to find the particular subsystem in which we're failing in. And I think that, without that insight, you can't grow the site in this way. Does that answer?
Thank you.
Okay, great.
Steve Trowgett, myself these days.
Hi.
Your first several slides, I was sitting back here getting all excited because they sounded like either you guys started with a good infrastructure configuration mindset at the beginning, or you learned a lot of hard lessons and then went looking for. How much of that was independent? How much was prior art? And
there were two sort of fortunate steps that happened. One was the early introduction of the configuration management system, and I think that we were very lucky in that we had a fairly world-class operations team from the outset. And yeah, we made a lot of mistakes. We had a lot of things that we did absolutely wrong. And I think anybody would when dealing with this scale. But having the configuration management system in place early, and also having probably around maybe 50 or 60 employees, I got very upset and I said, I'm never adding a password file again. And I wrote an LDAP system for dealing with machines and users. Those two steps allowed us to grow at a much faster rate than expected. But at the time, because we had taken on tools like Puppet that were in their infancy, we were probably debugging their tools as much as those authors were writing them. So that's kind of a lesson to be learned about taking that leap and doing, working with those tools early on. I think now, now Puppet is very mature. Chef is very mature. CF Engine has like 20 years of work behind it. We just didn't want to use CF Engine at the time because a few of us had a bad experience with it. So. Thanks.
Hi, Rowan Littell from Yahoo.
Hello.
Do you have the Scribe Hadoop patches available?
Yeah, they're available on GitHub.
Okay, I'd be very interested in
Yeah,
those.
they're awesome.
Thanks.
That's a lot of work coming from Travis Crawford and Kevin Wheel. They really kick butt.
Cool, thanks.
Hi, Chris Reiser from DreamWorks Animation.
Hello.
Do you have? You must have really good management support to allow you to work on projects like these, because sometimes it's hard. There's a disconnect between something like setting up Puppet. You know,
Well,
you know that it's going to benefit everybody, but
Yep.
but it's not obvious to everybody else.
Yeah, I would say that as as companies get larger, that these sort of state changes where you want to go from I have hundreds of files everywhere to I have this very dedicated configuration management system, that's a cultural change. And I think that that is a lot of what sort of the DevOps movement is about. It's about getting the cultural change of different teams that are fairly disparate working together to create a high-quality product. And yeah, our management has been very supportive, and we have people that are dedicated to open source, and it's one of the things that I really value about the culture at Twitter. Oh, sorry.
I'm Peter Hamilton. I'm from Brigham Young University's Supercomputing Lab.
Mm-hmm.
You talked a bit about acceptable failures, how looking at mean time to recovery instead of mean time to failure. What are things you guys have done to corners you've deemed acceptable to cut?
For example, I would say that the most obvious one would be like, how many web servers can I lose before I can't process traffic?
Yeah.
For those of you that use Nagios for system monitoring, one of the biggest problems about Nagios is that unless you build like massive dependency trees and you spend a lot of time going through and editing your configuration files, you get alerted for everything, right? So with us, it's like if I lost N% of my servers, I don't even want to alarm on them because I don't care. I can lose a certain number of web servers and still maintain the traffic load of the site plus some headroom. Databases are in a similar vein where like maybe I can lose a certain number of read slaves before the site is completely unusable. And in order to support something like this, you have to have like very, very fast timeouts. You have to say, if I make a request and I don't get a response in 50 milliseconds, throw it away. Just go to the next guy, mark that guy as dead, and don't come back to him. So there's this kind of careful dance going on between system failure and timeouts and monitoring.
Yeah, thank you.
Yeah, thanks.
Hi, I'm Nikolai Plum from Booking.com. You were talking about your review board and change process and so on. Do you have time to say a little bit about how much of that is a process control of people have to get approval and so on, and how much of it is a kind of agile change and other people keep an eye?
Yeah, interesting. So we have this thing where when you do your initial SVN commit, you're committing your change. It comes back and it says, review has been published, here's the URL for the review, and then we will typically have someone copy and paste that URL into IRC chat or wherever the admins happen to be hanging out. At that point in time, it is expected that you will get a ship it from at least one person on the team. If you're affecting a lot of systems, we would like to see multiple teams give you the okay to go ahead with that change. That being said, sometimes people make very small changes and they push them directly into production. So maybe you are making a change to a system that is not part of the main production tree. And we tend to frown on that. We want people to use the review system. And we typically expect to see in like your average commit message, when you do your final commit, we want to see reviewed by someone's name and then what you did. And we do have a post-commit hook that looks for the words reviewed by and a valid username. And if those three words don't exist, we just reject the commit altogether and we say, well, who are you? What are you talking about? And we also, like, if people put reviewed by me, we yell at them in the post-commit message. Let me say, well, reviewed by you? Really? No.
Thank you.
Oops. Watch your face.
It got me. Did you see
It attacks.
Did you, this might be hard to characterize, but how much overhead or how much timeline do you think is added by that review process?
Sometimes it can be a couple hours. And, sometimes it can be a day. That's unfortunate, but I think having the site not go down is more important. I will say that for those of you that are new to Puppet or any of these configuration management systems, that one of the hardest things that you have to deal with is that sometimes doing a very basic thing, like maybe you just want to make a symlink somewhere, might turn into like 10 or 20 lines of Puppet code or configuration code. And that adds a little more time. And if you do the wrong thing, if you make a mistake when editing your configuration and it's gone through the review process and then it's gone into production, and you're like, oh God, I made the wrong symlink, I made the wrong file name, the only kind of escape from that is to go through the process again. So it kind of raises the penalty on making mistakes a little bit, which is good.
Would you be able to characterize how much time, for instance, how much time do you spend writing change code versus actually sitting there reading other people's stuff in the review?
I don't know, like a review for me probably takes like a couple seconds. It's quick. It's like I just go, look, that's good, you didn't typo here, and I go to the next one. So, but actually, like writing code for change, we have an automated process that generates the change request, so no one writes that.
David Williamson, Microsoft Tell Me. This is clearly a very mature system at this point for scaling, for systems, but I was wondering how much of your network infrastructure is integrated into your kind of overall scaling and automation environment. You roll new systems, obviously at some point you're rolling new networks. Is that all integrated in, or is there independent separate tools, or is that manually built?
Yeah, most of this is in the same tools. We are just getting into the world where we're building networks and data centers and things like that, and moving out of sort of the co-located world, which we lived in for a long time. So we did do some automation. For example, our machine database, as an email would come in from our hosting provider that says, hey, you have a new computer, we would parse the email and inject it into our machine database and inject it into Puppet. So that kind of automated onboarding of systems is a huge, huge win. Instead of having your the co-location provider mail the ops team, they mail the automated system that then CCs us and injects the server.
So are you expecting in the future, as you build your own, to do like automatic deployment and installation for servers, routers, load balancers?
In fact, the majority of the router templates that we built so far are templated in this way.
Excellent.
So then we have tools that will go to those routers and inject things. There's a tool that Google wrote for doing template-based access control lists and routers, which you may be interested in. I think it's called, starts with a C, right? Yeah. It's like Kaida or something like that. Caprica, that's it. Yeah, like Caprica, but different. No robots. Thanks. See, someone knew that.
From Google. Can you comment a little bit about Scala? Is that something, it was a wise solution? Does it play a huge role in what you do?
Scala is a Java-like language that runs inside of the JVM. So the scaling constraints with Scala are known because we know how JVMs scale and we know how garbage collection functions. There are a number of things inside of Scala that are expressly designed for dealing with concurrency that our developers wanted to take advantage of. So that's kind of why they went with that. Also, Twitter has a fondness for kind of oddball functional languages. We have a lot of Ruby, we have a lot of crazy Python, and we have a fair amount of, well, we used to have Erlang, but we got rid of it. But we have some Scala and some Haskell floating out there. So a lot of people enjoy functional programming. So.
I see. Thank you.
All good?
Why don't we give John another round of applause?
Thank you.
Thank you very much.
Yeah.